Good. So then the topics for today are actually to finish the model formulation business now really. So that's the first thing. Finish GLM formulation. So you realize that we spent quite some time on formulating the model, which you might feel kind of unusual from what you've seen before in statistics, where it's basically you start with some data and then you compute stuff on the data. And we take quite an extensive amount of time to just talk about the model without regards to any kind of data. But that's completely in the intent of the course, and also to emphasize the importance of the model for everything that will follow then later, when of course we bring it together with data. So that's the first thing, and we have to still do some stuff in that regard. Then I want you, then based on that, I want to discuss again 2 examples for sampling the GLM, because this is also really important for your whole thinking about the inferences that we will do based on the GLM later on, especially in the frequentist sense. And then let's see how far we get. But then the next thing will, of course, be after model formulation will be model estimation or parameter estimation. And so depending on how far we go, we will start with an introduction to maximum likelihood estimation. Because that's the estimation technique that we are primarily interested in here in the winter term. Good, so that's the outline for today, and then let's get just started. So the first thing is again model formulation, and we got quite far already, which is good, so we don't start from scratch again. But let me briefly recap where we currently are. So we always have seen this equation, and we have now a good understanding of what this statement that I'm just writing here means, where epsilon is an n-dimensional real vector. So what does the statement imply that I just wrote? So this statement here, so basically what did we do? So I'm basically asking you about what we discussed in depth in the last hour of the course. So what does that intuitively mean, what I've written there?
The noise, the error term is distributed independently, and they have the same solution.
Identically. And can you say something more about how exactly the noise is distributed? I mean, you said the basic features, but...
According to the normal distribution.
And what are the parameters of this? You said they are all independently distributed and identically distributed, and you said according to a normal distribution, which is univariate, but what do you know about the parameters of that?
0 and because it's identical. Called the I matrix.
Identity matrix, but there is one thing. So it's not 1 because? Well, so the this statement here, that actually denotates the covariance matrix of this multivariate random variable, and it has, of course, a meaning for the variance of each marginal variable. So, and you said that the expectation of each of these marginal univariate variables is 0. But what is its variance? You said 1, but is it really 1? Somebody? Or 3?
And it's the covariance. I'm sure.
Yeah, so what I'm actually getting at, so never mind, so what I'm getting at is that the covariance matrix of this multivariate Gaussian looks as follows. So it has sigma square all over the diagonal. So the marginal variance and the variance of each of these epsilon I is in fact sigma square. That's maybe you're a little bit. So, what is the confusion? So you seem a little confused. Ask, why is that? Why do you think?
I'm just thinking about the standard case of the normal distribution where the mean is 0 and the sigma square is 1.
Yeah. Okay. I think the problem here is, and it's not a problem. The this symbol here, this sigma square, that doesn't mean variance of something. But this is a variable that can take on, that's a parameter variable that can take on different values. So sigma square can be 1, but it can also be 4, it cannot be negative. I think what you are confusing, which is of course fine, is, so there are two things, and this is actually important while we are at it, let's discuss it, because it's about these terms that one always uses. There are, maybe let's do that first, so some nomenclature, because that's actually fairly important, although I didn't plan for it. So there are these terms, expectation and variance, and then there are the terms expectation and variance parameter. And then there's definitely the term mean, and let's call it empirical variance. And the problem is here, it's just a language problem. It's not that you don't know, that you don't have the concepts associated with that, but that the language is not really clear. So I think it's very important to dissociate these three different cases when talking about things. So let's first talk about expectation and variance. Expectation and variance are analytical expressions that you can apply to analytical and theoretical concepts such as random variables, and only actually onto random variables. So if you have a random variable, so let x be x is a random variable. This is a mathematical construct. This is not in the real world. It's a mathematical model, and for example, it only says that x is some quantity that takes on some value. It's just a model for things that are outside in the world. So you can define whatever you want for this x. Now this x, this random variable, can be described by two numbers. One being the expectation of the random variable, which depending on what kind of random variable is, you compute in slightly different ways. But essentially you compute it, for example, if x has a probability density function by integrating x like this. So it's a completely analytical thing. So you don't need any data to compute the expectation of a random variable, because that's only happening in mathematics. Yeah? The same thing holds for the variance. So the variance of x is also a completely analytical quantity, which you get from, for example, integrating, depending on the type of random variable, by integrating x minus its expected value square dx and weighted by the probability. But again, how you in detail compute the expected value and variance, you might recall how we did it in the decision neuroscience course for lotteries, when everything is discrete. But this is something that you do completely irrespective of any kind of data or real world phenomena. Yeah, and that's what I mean when I say expectation and variance. Then there's something for the Gaussian where we have the thing that we say, okay, X has a multivariate distribution with an expectation parameter and a covariance parameter. The problem about the Gaussian in this sense, and because it's always introduced first, is that in this case, the parameters and the analytical quantities of the random variable are the same thing. So in fact, the expected value of X is mu, and the variance, or in this case, because it's multivariate, the covariance matrix of X is in fact sigma. But this does by no means hold for all probability distributions. So you can have probability distributions that have certain parameters. So maybe let's think of something that is called the beta distribution. So I'm not telling you actually what the beta distribution is. I'm just telling you that it has two parameters, A and B. And based on these parameters, you can compute the expectation of X by dividing A by A plus B, which means that in this case, the parameters of the probability distributions are not identical to the expectation of this random variable. Yeah? So this is just the problem with the Gaussian. In terms of teaching, it's a problem. Otherwise, it's completely great that it's like that. But in terms of teaching, it's the problem that it's then easy to confuse the analytical concept of variance and expectation from the parameters of a Gaussian, because these parameters you can always set. So you can define something for the covariance sigma, and you can define something for the mu here, and then you get a specific form of the Gaussian distribution. Again, here for a beta distribution, when formulating a model, you can define these parameters, which means that you can quite easily also evaluate the expected value of X in this case, but it's not identical to neither A or B. Yeah. And then the third thing, and this is maybe for you also maybe a little bit, it's on the one hand more familiar, but then of course also easier to confuse, is the mean and the empirical variance. These are these are kind of rules, descriptive statistics that you can apply if you have a data set. So for example, if you have a data set like this, 3.1, 2.9, 4.3 and 2.2, you can go ahead and compute the mean of this. So the mean, maybe we call that y. Let's not call y, then it's also confusing with everything else. Let's call that n for mean. That's horrible. Let's just call it mean, although I hate when people write words in equations. That always looks so unprofessional. So the mean you compute by summing these values and dividing by the number of values. So you have to compute 3.1 plus 2.9 plus 4.3 plus 2.2 and divide by 4. That's how you compute a mean based on this, and the variance, you know how to compute that because you did it in undergraduate statistics, and I don't want to go over it. So you have to use the mean and compute the squared deviations and divide, depending on which form you use for the empirical variance, divide by the number of values, so by 4, or if you use the non-biased version, by 3. Yeah, but it's so my convention is to be as precise as I can with the language. So when I say expectation and variance, I mean these analytical things that you can use and also quantify, of course, if you know the distribution of a random variable. The whole thing happens only in mathematics, only in your head, or if you use some tools to evaluate that in a computer, but without any data. But you have to do something. Expectation and variance parameters are the terms that I use for the parameters of the Gaussian, because how else call them? So you could call them elephant and kangaroo parameter to dissociate them more clearly from expectation and variance, but that's also not helpful. So I call them expectation and variance parameter. Based on these parameters, you can evaluate the expectation of a Gaussian random variable. It's just the expectation parameter, and you can evaluate the covariance of a Gaussian random variable. It's just the covariance parameter for the Gaussian, but not for other distributions. And finally, I really use the word mean because that's easy to dissociate it only for the case of computing a mean from data. So in this case, so I really avoid saying the mean of a Gaussian because that's, for me, that's not meaningful, although I know that a lot of people use that, but I'm a special person. So no, but it's really not meaningful because you can compute a mean on data, but if you have a Gaussian, this is a mathematical construct, so you cannot compute the mean from on that. And with variance, it's actually in standard deviation. Standard deviation has a strong connotation in actually descriptive statistics, much more than in model formulation. And maybe to dissociate variance in the mathematical sense and analytical sense from the variance that you can compute based on data, on some data set, which of course, and also don't forget this, you can always compute a mean and a variance completely regardless whether you have some model in your head that is has something to do with a Gaussian. So that's also important to note, of course. But for for the variance that you compute on data, I call that empirical variance. Yeah. So three very different concepts that it helps to dissociate. Yeah. Questions about these dissociation or criticism or confusion? No. Good. So then coming back to the reason that started that. So I think you regarded this thing that I wrote here, the sigma square, maybe as this, so as a symbol for the concept of the variance. Yes?
Yeah, confuse it with the standard normal distribution.
Or you confuse it with the standard normal distribution, which would mean that sigma square is actually 1. But then, of course, one could just write 1, and one need to put a sigma square there. Yeah. Okay. And it's also important that it's not 1 because the sigma square is a parameter of the GLM, and if it always would be 1, you would always make the assumption that the error variance is actually 1, and of course that's a fairly strong constraint for modeling data if you always think that the variance is 1, so you can have different variances. Okay, so but it's good that we also talked about that because that's important. And important also to dissociate in your head. Okay, but we then let's start again. So we have our x beta plus epsilon, and the epsilon is distributed according to a multivariate Gaussian over epsilon with expectation parameter 0 and covariance matrix sigma square, which is a scalar times in. So sigma square must be larger than 0. This kind of notation that you have a small letter that's larger than 0, this implies also that sigma square is a scalar. I find it a little bit surprising, but that's how the mathematical literature is. So this, if you see something like this, this usually means that sigma square is larger than 0. Otherwise, you wouldn't need to define what you actually mean by the larger than sign for something that is multivariate, which of course can be done. Now we discussed what this means, and we just recapitulated that. What this means is that the components, so epsilon I, all of them are distributed according to univariate Gaussians, again with expectation 0 and with variance expectation parameter and variance parameter sigma square. The notation is relatively clear. The only problem is here the 0, because the 0 here actually is a n-dimensional vector with all zeros, and here the 0 is just the 0 that you know. Yeah, one can deal with that. Another way to write this is actually to use a 0n here. Maybe I should actually change that. It's not the most common thing that you see, but you can of course call that 0n, but then you need to define somewhere that by 0n you mean, I'm sliding over my thing here, you mean a vector of n zeros. Yeah? You might find this all a little bit picky and nitty-gritty, but if I ask you to implement this on a computer, you have no chance if you don't know what the symbols actually mean. That was the question.
If there's no noise, can the variance also be 0?
No, the Gaussian, the probability density function of the Gaussian requires that the variance is larger than 0. So if you think in terms of the univariate case, you know that you have this thing there, 2 pi sigma square. 2 pi sigma square. And if you have 0 there, I'm not quite sure, is the square root defined for 0 or not? I'm not sure whether it is, but if it is defined, the only sensible thing is that you get 1 over 0, which might already be not defined if sigma square is, if the 0 is not a possible argument for the square root, but I'm not quite sure at the present. If it is a possible argument, the only reasonable thing is 0, and then you divide by 0. So while you of course can have the case that you observe data that is all identical, so you observe something like this, and you can compute an empirical variance from this, which of course would be 0, the Gaussian does not model the case of no variance. And there is this what people like to talk about is that the Dirac delta function is kind of the limiting case of a Gaussian, so that you have something looking like that instead of something looking like that. But really, this also doesn't really work. So the Dirac delta function is not a probability density function, and it all goes horribly wrong if you try to do that, as we experienced with our variational base paper. So just doesn't, in this case, is not modeled by a Gaussian. If you want a model that has no variance, you cannot use the Gaussian. You can also not use the Gaussian if you want to model a uniform distribution, because that's also not working with the Gaussian. It's just not mathematically defined. Good. Other question? No. Good. So then we are at this point now. And what I actually want to get at is that we think about what the definition of the epsilon I, where we now know that all the epsilon I are identically and independently distributed, so IID, I from 1 to n, what that means actually for the thing that we care a little bit more about than the noise, namely the thing that we use to model the data, so the y. And to illustrate that, let's maybe first start with an example. So what you see here, of course, now if I tell you that, so of course you know from the other times that X is n times P matrix, beta is a P-dimensional vector, and then the realizations are n-dimensional vectors. So if I now tell you n is, for example, 3, then of course you know that this thing here means that you have something like this, y1 equals, and we've seen before that this x beta actually results in a n-dimensional vector. So which one might as well call mu. So then the components are mu I, and this is the first component. So we get this, and this. And what and of course the epsilons are distributed according to that. So what I want to stress here is that the yi, so y1, y2, y3 in this concrete example, is created by adding a realization of a random variable to something that is non-stochastic. Yeah, so this is non-stochastic. This is defined in terms of the design matrix and the parameter values, and this is stochastic. So this is a random variable. And the question is now what this means for what is on the left side of this equation. So maybe let's do an example. Let's say our mu is let's say 1, 2, 3. So mu1 is 1, mu2 is 2, and mu3 is 3. Or maybe let's make it a little bit more advanced. So mu3 is actually 4, so that you don't confuse the index with the values it takes on. And we now want to compute the values of y1, y2, y3. So we have y1 equals 1 plus, and now we have this epsilon 1, and if we want to compute something there, we need to sample this random variable. Yeah, and this, how can we sample this random variable? Well, we can use a random number generator implemented in, for example, some computer. But as we also did before, we can also be our own random number generator. But we should think a little bit about what happens most of the time. So, of course, our epsilon I, they are distributed according to a univariate Gaussian. This now what we need to specify even in our heads in a way, but although nobody will ever check whether the random numbers that we now generate here actually conform to the distribution that we say they conform to, but we should at least make it kind of sensible. We might as well say that our sigma square is, I don't know, let's use 1. So that 63% of the probability mass are actually between -1 and 1. So that we now, when we sample in our head, we don't sample plus 7,220,163, but rather we sample something like 0.01. Yeah, it's more likely than the 7 million stuff. Let's do that again. So we have 2. Let's say we sample something negative now. So we sample minus 0.5, and y3 we sample plus 0.2. So we sample these values. Now our y values are actually 1.1. 1.5 and 4 times 4.02. So what I'm trying to illustrate here is that if you add something stochastic, so this is random or stochastic, random, to something that is deterministic, the outcome, so this thing, do you want to vote? Who is for deterministic? Who's for random? And there are a lot of non-decisions, but at least there's a majority for random. So it actually, in terms of mathematical modeling and also from the intuition that you've seen here, this also becomes random because you can just think, okay, we have something deterministic that's always, let's say, 4, and then somebody tells us a random number that we have to add to it. Of course, what we then get is also random. Of course, the deterministic part still plays a role, but there's a random contribution, and so it's random. mathematically, we can also think about it, maybe first, not really mathematically, but kind of intuitive. If we think again about a Gaussian, that univariate that is centered on 0, and maybe let's go a little bit further here, and we sample value from it. So let's draw a random number, almost. Let's draw a random number, and let's draw another one, and another one, and another one, and another one. If we now do what we actually wrote there, that we always add to each realization of this random number, which is of course here meant to represent the epsilon I. So this is the epsilon I. And we add to each of these values something deterministic. Let's say 2. There we had different values, but let's say we just add 2 all the time. Then, of course, we can think what actually happened, can think about what actually happens. So let's say this is 1 and this is 2 on the axis here. And we want to add to each of these realizations, we want to add 2 to get something, let's call it zeta I. We want to add 2. That means if we have this value, which is, I don't know, 0.2 maybe, when we add 2, where do we get? So let's say that this is actually in fact 0.2. Which value do we get if we add 2? Okay. What? 2 or 2.2 exactly? So we get here, let's say that this value is 0.1. If we add 2, what do we get? 2.1. If this might be, let's say, minus 0.15, if we add 2, what do we get? So we get this. This might be minus 0.2, so if we add 2, what do we get?
I'm sorry, I have a question. Why are we adding numbers? I don't understand what these numbers represent.
We're adding numbers because I want to explain, because it's fun to add numbers. Because that's what mathematicians do, they add numbers. No, because I want to explain what this means in terms of why. And give me a little bit of time, then it will be clear. Yeah. Okay. Again, so this is minus 0.2. If we add 2 to it, what do we get? 1.8. Then we have this value here, which might be minus 0.9. So we get 1.1. Now, what you've seen here is that we did kind of this transform over there. So we added plus 2 to all of our values. And what I want you now to infer visually is that, of course, here we sample a lot of values here and relatively few on the sides. So if we draw all these values here, we get a lot of values here around 2 and relatively few on the side. Now, if we think about the probability distribution that actually, or the probability density function that actually represents these realizations, what do you think will we get there?
Like how
will it look? The same?
But further over?
But further over, exactly. That's one way to say it. The same, but further over. That's definitely the case. So it looks like the Gaussian, but it's centered on 2. Yeah. And this is exactly, this one can generalize in many ways. And so what this essentially means is the following. If we have, let's say, n, so let's say x is a scalar random variable, and it is centered, so its expectation parameter is 0, and it has a certain variance. Then if we define z to be x plus a fixed value, let's call it b being a non-random quantity, a deterministic thing, like I wrote 2 here, that was not random, that was always 2, then z is distributed again according to a univariate Gaussian with which expectation parameter? B, exactly, because what you did here is you did always added 2, and here, if you think about the expectation parameter, it was 0 here, and you inferred that the expectation parameter is 2 here, so you can either view it as 0 plus B, and then of course you know that that's B. And the variance I don't ask you, because that's not necessarily trivial. In fact, the variance is again sigma square. That doesn't hold if you actually multiply the x. So for example, if you have another parameter here that multiplies the x, then actually the variance increases as a in the square of a. So you actually get a square times a sigma square. The whole thing that we are doing here is actually, that might look quite simple, but if you look into mathematical books, what we are doing here is we transform a random variable and ask about its distribution. So here we have a random variable with a probability density function, and then we apply a function to it. In this case, we just add something to it, and then we ask what is the probability density function of the resulting random variable. That's actually not trivial, and I mean, for example, a very famous case that you're all familiar with, but you might not realize that this is the case, is the t-distribution, which is actually the famous paper by a student who described the t-distribution. That was not like, hey guys, I discovered the t-test, but it was actually a derivation of the t-distribution based on the assumptions that go into the basic distribution about the noise, and then the functions that apply to it. We will see that later. But it's actually not that easy to derive. So in general, it's not that easy to derive the probability density function of a random variable that you apply some, often then also nonlinear function to. But here it's relatively straightforward, and actually also quite important for what we will do in the following. So this is also why I want to generalize this to a certain degree, and introduce now something that's called the linear transformation theorem. For the Gaussian. And this is just a mathematical result that I just state, and you can basically look into proofs of that if you feel like it, but you can also just take it because there are two things. One is always understanding what a theorem wants to say, and the other one is to actually understand where it's coming from. So one thing that we will need on a couple of occasions during the course is the following statement. So if y is now again a multivariate thing, you could call it differently, but I call it y for the moment, and mu y is also an n-dimensional vector, and sigma y is a positive definite matrix that is n by n, and A actually is an m times n dimensional matrix, and what else do we need? B. B is an n dimensional vector, And we have the case that y is distributed according to a multivariate Gaussian distribution with expectation parameter mu y and covariance parameter sigma y. This is why I defined this bit here. And now we want to apply a function to y, and we do that by actually defining the value that this function takes on. Namely, we define z as a times y plus b. So what this means is whenever we get a realization of y from this distribution, we should multiply this realization with A, this matrix, and add to, so that's this bit, and add to the result this vector b, and of course A and b are given to us. If this is the case, then z is distributed according, again, to a multivariate Gaussian distribution over z. Actually, that's something. Oh, sorry. I wanted to ask you something, but now I fucked it up myself, so I don't ask you because I wanted to ask you about the dimensionality of z. And of course, if A is m times n, then the result of this thing is an m-dimensional vector, so it's not meaningful to add an n-dimensional thing to it. So this is why this was wrong, and of course B needs to be m-dimensional, so Z is m-dimensional. If Z is distributed according to an m-dimensional Gaussian distribution with expectation parameter given by A times the expectation parameter of y, so expectation parameter A times mu y, which makes sense. So mu y is n-dimensional, A is m times n-dimensional, so you get an m-dimensional thing out of it. And covariance matrix given by A times sigma y times the transpose of A. So if you think about this, this is m times n times n times n times, this is the transpose of A, so n times m. And then if you do apply this little rule from matrix algebra, what you actually get and find is that this is an m times m matrix, which makes sense if Z is an m-dimensional random variable, and that's what the linear transformation theorem says. So again, and what is so nice about this theorem, which one can of course prove, is that if you know the parameters of the distribution of y, so if you know mu y and you know sigma y, and you know the parameters of your function that you want to apply, namely that you want to multiply it by a matrix R and a parameter B, then you already know the distribution of the resulting random variable, namely that its expectation parameter, here mu z, is A times mu y, and its covariance parameter, looks a little horrible, but anyway, sigma z is given by A times sigma y times AT. So this was now the generalization of what we just did for the univariate case. It's completely the same thing. You just, oh, am I forgetting something? Oh, I'm fucking up all the time here. Plus B, of course. So, of course, you need to multiply the expectation parameter, but you, of course, need to add the plus B here, because that is essentially what we did up here. So here we actually multiplied all these values by 1. So here our A was 1 and our B was 2, right? So we multiplied all of these values with 1, which doesn't make a difference, and we then added 2. So of course the expectation parameter of mu z is this. and the covariance parameter, and that's correct, that is independent of the bias, that's that. So yeah, so I think I'm happy, and I hope I didn't confuse you too much. The nice thing is still that you know the parameters of this, you know the parameters of your function a and b, and then you know the parameters of the resulting Gaussian random variable. Good. Any other mistakes that I made when presenting this that you want to point out?
I'm not clear about this part, the arrow part in the Z.
This thing?
No, this part. And that part. Why you want to cross the A transformation matrix here?
What are you confused about? This?
Yeah, this part. And the arrow part. Yeah.
And the arrow part. Now I understand. Yeah. Sorry, I was thinking about an arrow. That was my problem. But you mean the error, which I just didn't understand because I didn't make the inference. So you basically want to know how this relates to what we've seen upstairs. Yeah, upstairs is good. So what we've seen here. Yeah, and that's actually fairly important. So let's do it. What we have written up there was the following. That we have this case. And now you have to think in terms of what's happening here. So you have to completely dissociate now the denotation from actually the concept, because it actually is different in terms of the denotation than what we actually do in the GLM. So what we are doing here is that we have an n-dimensional random variable epsilon, and we add to that x beta, which is a vector. So we do our function that we actually do is we define our new random variable as y being our epsilon plus a vector, and this vector is given by x beta. Yeah, I mean, it's just the same thing as written above there, just in the other order. So the matrix R that we actually apply here is the identity matrix. So we could also, of course, put an IN in front of that. So then we would have again epsilon, and then we add this x beta. And it's exactly what you said is the important thing, because we now know something about the distribution of y, namely that it's also n-dimensional and multivariate Gaussian distributed. This we know from this linear transformation theorem. Then we know something about its expectation, because here we've seen that, maybe I'll use a color, that it's the expectation of the original random variable, which was epsilon, so that was 0. That's 0. Our A is the identity matrix, so we actually do IN times 0, which again gives the 0 vector, plus B, and our bias in this case, or not bias, but our B vector is x beta. So the resulting expectation parameter here is 0 plus x beta, which is just x beta. And because our A matrix is the identity matrix, our resulting covariance matrix is A. Oh, no, A is clear, that's what it says up there, but it's IN times sigma square in times in transpose. Now, multiplication with the identity matrix doesn't have an effect on the matrix that is it's multiplied with, so we can get rid of that. The transpose of the identity matrix is again the identity matrix, so we have a multiplication again with the identity matrix, which we can also get rid of. So we have sigma square, let's get rid of this here, sigma square in. Oh, I have to stop. And that's actually where I wanted to get at. Yeah, so this, and we can also get rid of that. The fact that that we define in the GLM y to be x beta plus epsilon, and epsilon is distributed according to multivariate Gaussian with expectation parameter z and 0 and covariance parameter sigma square in, is equivalent. So that's the is basically the same statement to the fact that y, so the thing that we use to model our data, is distributed according to a multivariate Gaussian with expectation parameter x beta, so given by our design matrix and the parameter values, and covariance matrix sigma square in. And that's really crucial, and this is basically where we will continue from now on. Yeah. So to get there, what I try to do is give you some intuition about adding numbers to realizations of a univariate random variable. Then, out of my mathematician head, I drew the linear transformation theorem, which is just essentially the generalization of what we then did. And if you feel like it, you can look up the proof. I think the expectation parameter is quite straightforward. The covariance parameter is a little bit less straightforward. And then we applied this linear transformation theorem now in the last part to the case that we always discussed. So that we have some deterministic aspects here and some error here. We know something about the error, and this means that we know something about the stuff that we will use to model data. Okay, questions right now? Because otherwise we should take a break now. Good, then let's take a break.